So here we're looking at Chapter 2 in SER230 or 222. We're using the book Java Software Structures by Lewis and Chase. You can use the 3rd edition or the 4th edition. And this one's on analysis of algorithms. We're going to talk a little bit about what efficiency means and efficiency goals. We're going to talk about the concept of algorithm analysis, and we're going to introduce or reintroduce, because everybody in this class should have taken a class called Math 243 or Discrete Mathematics that introduced the concept of big O notation. But my understanding is you maybe got a week of it and forgot it all already. So we're going to review that and the concept of asymptotic complexity and how we compare growth functions, really how we compare and classify and categorize algorithms based off of their efficiency. So what do we mean by efficiency? Usually we're talking about the amount of time it takes, or not maybe the wall clock time or the CPU time. But the problem with measuring CPU time is your computers generally get faster over time. You know, Moore's law, I forget how often computers kept doubling in speed for a long time, and that's kind of trailing off, I think. It has to. So you get this free improvement in efficiency. So, and plus, your computer might be twice as fast as his computer, etc. So sometimes we're actually going to measure efficiency in terms of how many instructions need to be executed, because that stays the same no matter what happens to your CPU. But then again, it might change again based on how exactly the algorithm's implemented, and it might be too detailed for us. So we're going to look at how we categorize algorithms in broad strokes in terms of their levels of efficiency, without getting into the precise number of operations. And we're going to look at an everyday example, which is washing dishes. So here we go. Here's the example. Washing a dish takes 30 seconds. Let me shrink my beautiful face. So washing a dish takes 30 seconds. Drying a dish, an additional 30 seconds. Therefore, how long does it take to wash n dishes? Well, n times 30 for washing plus n times 30 for drying. Right? So we can count the number of wash and dry operations plus how long each operation takes. Hopefully we get n minutes, right? But there's a stupider way to do it. A way that I hope none of you would do it, but you know, one could choose to do it this way. That's a much less efficient approach where every time you wash one dish, you splash dirt all over the rest of them, or something. Like you splash water all over the rest of the dish. So you have to dry all of the previous dishes. Okay, then you go and you wash the next dish, and while you're washing that dish, you splash water all over the dishes you'd already dried. So you have to dry them all again. So each time you wash one dish, you have to dry not only that dish, but every dish you'd already dried before. So how does that work? Well, you spend 30 seconds washing each dish. For the first dish, you only have to dry one dish. On the second dish, you have to dry that dish plus the other one. So 2 dishes. On the third dish, you have to dry that dish and then the previous 2. So 3 dishes. On the 4th time, you have to dry 4 dishes. So what we end up with is n times 30 seconds for washing, and we have 30 seconds times 1 plus 2 plus 3 plus 4, summing up all the way up to plus n. So that whole summation we're writing here on this slide using a sigma. So this is read the sum from I equals 1 to n of I, and it's times 30. This 30 could have been factored out. Right? So the interesting thing, and this is something you, I think it's in the appendix I asked you to read or something. This is called an arithmetic series. Google it, wiki it. We hate summations generally. You don't want to leave them there. You want to get rid of them. Fortunately, the sum I equals 1 to n of I is equal to n times n plus 1 over 2. This is an arithmetic series. Remember it comes up a lot in analysis of algorithms. Whenever you see it, you just replace it by n times n plus 1 over 2. So the amount of time that it actually takes, if you distribute this out, this is 30n squared plus 30n over 2. So we've got 30n plus 15n is 15n seconds, and we have 30n squared over 2, so 15n squared plus 45n seconds. So we have pretty much analyzed and gotten the exact number of seconds it takes to wash dishes using this approach. It's not a very good approach. There are some better examples that I would like to talk about in terms of analyzing algorithms, but what I'd like to point out is if you look at the number of seconds this takes, you'll find that it's very bad. So I'm not going to go over these examples right now. I'm going to skip it. When I present this live in class, I show how this works, but I'm going to skip it right now, and I can point you at a video that gives these examples. So in the previous one for washing dishes, there was n, the number of dishes, which is our concept of the problem size. So generally when we're looking at an algorithm, it deals with a collection of stuff, right, a bunch of them. You have to have some notion of the size n, in this case the number of dishes. The size of the algorithm, what you use to represent the size can change based off of the problem. For a search algorithm, if you've got 100 numbers and you're searching to see if the number 7 is in there anywhere, then the number of different things you have, the size of your search pool becomes the size of the problem. For a sorting algorithm, the number of elements that you have to sort, right? So there's a bunch. So if in ours it's the number of dishes, right? And then also you got to decide what you're going to optimize. So on a computer, you've got some resources, some hardware resources that are very constrained. One is time. So generally, you want to be responsive enough that users don't have to wait for hours to get the answer. And space. We usually have a small, although memory is cheaper. Memory can be bought. Multiple CPUs can also be bought, but it's harder to parallelize algorithms and so forth. But it's easy to just add memory and throw memory in it, but we still want to think about space complexity. Usually we're worried about CPU time. And what it turns out that some algorithms are so much worse than others that you can just throw out the details and focus on the highest order term to analyze them, because they're so bad that relative to the other problem, the one problem is it looks like it takes no time at all relative to the other, right? So when we're looking at growth functions show how much problems blow up as the size of the problem increases. So how much do they blow up? Right? So the growth function of the second dishwashing algorithm is t of n, so we're looking at time of n, and it's the formula 15n squared plus 45n, so that's the time in seconds. That's very precise. It tells you exactly how many seconds, but it's more detail than we typically need. That 45n is not necessary. We're mainly interested in the asymptotic complexity algorithm, which is the general nature of the algorithm as n increases. Or another way to think of it, if we know that n never gets bigger than 10, then I could tell you exactly how much time this algorithm takes in the worst case. But I don't know that n never gets bigger than 10. N might get bigger. N might be 100, right? Actually, you pick any n, and you could make it a little bit bigger. So for which n do we analyze this problem? So what we're going to do is we're going to say, well, for n getting arbitrarily large, what we're really looking at is what's the performance like kind of in the limit as n approaches infinity. All right? So in fact, in the limit as n approaches infinity, this guy is relative to that guy is 0. Right? This guy's n approaches infinity, right? So take him, divide it by that, and you get something like 1 over n. And as n goes to infinity, that goes down to 0. And this has no impact. So all that really matters is the n squared term, the highest order term. That's what we're talking about when we say asymptotic complexity. We're looking at the limit of the performance as n hits infinity. Just to give you a little bit more on the idea. We're looking at the dominant term of the growth function, the term that increases the most quickly as n increases. So the dominant term in the second dishwashing algorithm is n squared. We have this term, which is 15n squared and 45n. And as n is small, we can see that this term is smaller than this term. But very quickly, this n squared term catches up to and then surpasses this term. And before long, we're looking at, so this guy is like 15 million times bigger than this term. And it's only going to widen, the gap is only going to widen. So this guy actually, it's not just bigger, he grows bigger. So he's actually smaller here. He grows faster than this term. So when we're analyzing algorithms, we're concerned with how much they blow up in the worst case. And so we're going to look at this dominant term. This is worse than this, that n squared thing. Right? So big O notation is how we analyze these things. The coefficients, the constant factors, and the lower order terms become increasingly less relevant as n increases. They just don't matter as much. They disappear in the limit. So weird things happen as you take limits, right? So we say that the algorithm is order n squared, written big O of n squared, and this is called big O of a notation. And we say it's n squared because the dominant term is some constant times n squared. Right. There are various big O categories. So there are functions which bound our runtime. They're above. Some constant times this function always stays above our function's performance. Two algorithms that are in the same category are generally considered to have the same efficiency, but that doesn't mean their growth functions are equal, or that they behave the same for all values of n. What we're doing with these things is we're throwing away those details, like the 15n, and we're doing that, or whatever, 45n. We're throwing away the details so we can make a broad strokes comparison. And the reason is because you can do that quickly before you've implemented it without having to have an algorithm, without even having to count all the operations precisely. You can do this kind of analysis on the back of a napkin when you're planning it. So that's why we do it. And if you can find a big O difference between two algorithms, that's huge. When you have two algorithms that have the same asymptotic complexity, then you might want to drill down and count more operations in more detail. But first, we want to do this kind of big O analysis, and usually that's what matters the most, anyway, because big O is things shoot off towards infinity or down to zero, So here's some example of growth, some sample growth functions and their big O categories. So if you have a constant like t of n is 17, an example of an algorithm that has constant performance would be to find the median value in an array. So if you need to find the median value in a sorted array, assume that the array is sorted already on input because sorting is not constant. But if you're given a sorted list of numbers and you know that it's sorted somehow, maybe it's the finish times of a race, right? And you want to find the median value, then all you have to do is a little arithmetic, right? So if you know that there's n values, you look at position n over 2. Boom, there's the median. That's a constant time operation, no matter what. If you have an algorithm that is like the t of n, it takes 3 times the log of n operations to do. So an example of an algorithm that might take the log of n. So the logarithm of n tells you how many times you can keep dividing n in half before you hit 1. Right? So for 8, you can divide it in half and get 4. You divide it in half and get 2. You divide it in half one more time, you get 1. So the log of 8 is 3. Right? So the log of 1 is 0. The log of 2 is 1. The log of 4, and so forth. Right? So 2 to the what equals n. So, and the reason that the log of n shows up a lot in big O is because so many algorithms work by taking a big list of numbers and trying to eliminate half of them from being considered. And it turns out you can eliminate more than half each time. But as long as you always eliminate a constant amount, you end up with a log n performance. An example of an algorithm with log n performance is binary search. So where binary search says if you've got a sorted list of numbers, you look in the middle, and if the thing in the middle is greater than the one that you're looking for, then you only have to search through the first half. Otherwise, you only have to search through the second half. So each time you split the pool of things you need to consider in half with a binary search, and you end up with a log n algorithm, right? So log n grows faster than a constant algorithm. And then you have order n algorithms. So an order n algorithm is most algorithms where you need to look at every element. So if you have an unsorted list of numbers and you need to find the maximum value, well, there's no way to do that without looking at every single element at least once. So you have to pass through them all once. So that gives you an order n algorithm. Another category is n log n. Algorithms which are n log n, they again can be, very often there's that logarithm in there, and a logarithm is a big hint that you're using divide and conquer. You're splitting the collection in half, doing something, right? And then maybe piecing them back together. So n log n algorithms, a lot of your search algorithms would be n log n, right? So searching through, in order to, not search, a lot of your sorting algorithms would be n log n, where you can split the collection in half, sort one half, sort the other half, and somehow put them together again. So how many times, putting them together again costs you n operations, and then you have to do that every time you split them in half. So you end up with n times log n operations for sorting, right? N squared algorithms. Again, a less efficient type of sorting could be n squared. So that dishwashing algorithm was an n squared algorithm, an order n squared algorithm. You have cubic algorithms, order n cubed. So for instance, a really important one is matrix multiplication. If you haven't taken linear algebra yet, matrices are used for a lot of numerical simulation, physical modeling, etc. They're really important, and multiplying two matrices using the normal method is order n cubed, although people have been able to find slightly faster methods, but not this fast. And then there's these algorithms, which, you can have, these are all polynomial, so we're going to call these quadratic, cubic, but really any algorithm which is n raised to a power or less is kind of polynomial time. N log n is better than n squared, worse than n. And then the worst down here this is called exponential, 2 raised to the n. So an algorithm which is order 2 to the n, you can't solve it. There's a very small limit to what you can do. So an example of this is some of your games and some stuff in cryptography. These are algorithms that are so difficult that they'll use them in cryptography to make it so that nobody can crack it, because in order to crack it, you'd have to solve an exponential time algorithm. Things like the Towers of Hanoi puzzle, this game where you have 3 pegs and you have to move all the pegs from one to the other without stacking a bigger peg on a smaller. Google Towers of Hanoi. Look at it. It's a 2 to the n algorithm, and the mythology is that if you were able to do it with something like 10 or 30, there were 30 disks. If you could do it for a problem size of n equals 30, the universe would end, because it really probably would. It would take that long. So when you're comparing growth functions, you might think that it's a waste of time. Who cares about performance? Faster processors make efficient algorithms less important. That's true. That is true. Faster algorithms will cause your algorithm to speed up. However, this big O is capturing something which is such a large difference in performance that speeding up a processor double or 10 times really does not increase the size of a problem you can solve if your algorithm isn't actually efficient. So just to have a little look, if you have an order n algorithm, then you can solve problems of size S1 before speeding it up. And now you get on a processor which is 10 times as faster, you can solve a problem that's 10 times as big. If you have a problem whose time complexity is n squared, so when you speed up the processor 10 times, the size of the problem you can solve is only a little bit more than 3 times as big. And actually, this is, I think this is the square root of 10. So you've got, S1 plus what squared equals 10 S1 squared. And you just take the square root of both sides. You get 3.16. So it doesn't, it's kind of inverse to that, square root, right? So same thing with n cubed, right? So if you've got a problem, a complexity of n cubed, if you can solve a problem of size S3 with time S3 cubed, right? Then with 10 times as much time, so S1 plus what cubed equals 10 S3 cubed, and you get this cubed root of 10, 2.15. You could work that out. 2.15 raised to the third power would be 10. So it really, you get less payoff, kind of exponentially less payoff as the time complexity increases from linear to quadratic to cubic. And then really in the worst case here, you've got a 2 to the n algorithm, an exponential algorithm. So if you can solve, so you have 2 raised to the S4 is your original amount of time, and with a computer which is 10 times as fast, you have 10 times 2 raised to the S4. Well, what is the exponent there? 2 raised to the what is going to get you 10. Well, 2 raised to the 3.3 log of 10 is what gets you there. So it's actually only adding, because this S4 was in the exponent, it's only adding 3.3 to the problem size you can solve, log of 10, to the problem size, or log base 2 of 10 to the problem size you can solve. So you're getting even less payoff when you have exponential time complexity. So I think you've got a homework assignment to work that out, and if you could understand what I was saying, I probably gave you the answers. I think, okay, so let's look here. So when we're comparing growth functions, it's important, I mean, plotting these things is a good exercise and maybe gives you some intuition of what's going on. In this plot, we can see that as the input size, which is on the bottom, increases, we're looking at the amount of time it takes. And down here at the bottom, we have an order log n algorithm right here, that dotted line. And then above it, we have an order n algorithm. And then there's an order n to the log of r algorithm, which I can't even see, n times the log of r. There's n squared, n cubed, and we have here 2 raised to the nth power. I've got that backwards. This is n cubed and this is 2 raised to the nth power. So n cubed and 2 raised to the nth power. So plotting them is good, and if you're looking at this, it seems like, at about, 5 or 6 seconds, the algorithm which is faster is 2 to the nth power, because n cubed takes a lot more time at that point. But that's deceptive, because as n increases, if we look at the next slide, these things shuffle. So now we're kind of zoomed out. Okay, going back to the previous slide, this only got you up to size n equals 25. That's not a very big problem size. When we start to look at bigger problem sizes of like 100 or 200, we see a very different story. So for small n, 2 to the n actually seemed better than n cubed. But here we see that n cubed, for slightly bigger, starts to look significantly better than 2 to the n. I mean, n cubed right here, I don't know where that is up in the maybe 40,000 range, whereas 2 to the n is, goodness, it doesn't even fit in the plot. And down here what's happened, if we go back and forth, we look at these plots. In order to fit the bigger running times into the plot, we had to scale the plot vertically. which makes this order n algorithm begin to look, see it looks a lot more like it takes no time at all. So the order n algorithm and the order n log of n and log of n algorithms all down here, those all look effectively like they take no time at all. Whereas this one, which is n squared, we still see it taking some time. So relative to n squared, an order n algorithm begins to look like it's free. It takes no time at all. And of course, relative to n cubed, an n squared algorithm would eventually begin to look as if it took no time at all as well. So that's what we're looking at with asymptotic complexity. You're really using it to compare two functions. In the limit, one of them is going to look like 0, and the other is going to look like infinity. So the infinity one takes more time. Don't pick that one. The one that looks like it's 0 relative is going to be the winner. Unless they're both within some constant. If in the limit you get some constant, that means both algorithms are equivalent asymptotically. And then you might want to get into more detail. What does this mean when we're looking at code? How do we determine this runtime when we're looking at code instead of washing dishes? So the trick is, first, you want to look at you want to do this when we're looking at loops, like for loops, which is going to be the most common thing, or while loops. What you're going to want to do to analyze your code is you're going to start with the most nested loop, the innermost loop, and figure out how much time that takes, and work your way out, multiplying. So here's the example. So you have a for loop, and inside the body of the for loop, you have something which takes big O of 1 steps. And we don't need to be precise, just asymptotic, big O of 1 steps. And if we're going to do that n times, then what we're going to get is n times big O of 1, which is big O of n efficiency. Right? So when you have a while loop, so here we've got a while loop, and we got to figure out how many times this loop executes. So we're going to start with count equaling 1, and we're going to double count. And we want to figure out how many times can we double the count before we pass n. So again, it's a logarithm thing, right? So how many 2 raised to what power equals n? And that's really the definition of the log of n, or at least the log base 2 of n. So whenever we see something where how many times can you double it before you hit n, or how many times can you divide n by 2, those are things where log n is going to be the answer. Hopefully you can see that. You can kind of test it, right? So if n is 8, you have 1, 2, 4, and then you hit 8, so you fail it. So you do it 3 times. So the log of 8 is 3. 2 to the third is 8. So you see how that works. When you have nested loops, you're going to look at the innermost loop and work your way out. So here we have some sequence of order 1 steps, and we do it n times. So this whole chunk of code here is order n. And we do that, again, n times. So we get n squared as the final performance. If you have a routine that calls other methods or other functions in the body of a routine, you look for the most expensive, the largest big O, and that's the one that counts. So if you have a routine and it calls method 1 is order 1, then method 2 is order 1, method 2 is order n squared, and method 3 is order n. Well, the big O is going to be the worst of those. Just like if you're adding them all together, you take the fastest growing term. So it's going to be the n squared method in that example. The fastest growing one is going to be the performance of your algorithm. So the method call itself is free. It takes a constant amount of overhead. So that kind of wraps up analysis. This is a hard topic. I expect some discussion on it to happen on the course discussion board.